Hello. The goal of this lab is to find unknown forces by using motion observations of a visible star orbiting around a black hole using Newton's second law as shown here, and then apply Newton's universal law of gravitation to solve for the unknown mass of the black hole by the formula shown here. The net force of gravity by the black hole on the star is proportional to the product of their masses and inversely proportional to the square of the distance between them. The data used to initialize the Python program was the mass of the star, location of the black hole, motion data of the star as provided by Georgia Tech in the list of XY positions in the stardata.csv file. Time between each observation delta t is 1 Earth day. The interactions in the system. We assume that the net force on the system is solely due to the gravitational force of the black hole. I'll create a model using VPython to simulate the motion of the star around the black hole and show a visual representation of the net force and its parallel and perpendicular components using scaled colored arrows along the trajectory. Here are some key excerpts of my Python code. The green boxes point to important lines of code. The first green box on the top here shows how I iteratively compute x and y components of velocity of the star at every position data point provided for each Earth day, as pointed to by the green arrow. These lines of code show the calculation of the initial and final momentum of the star and the rate of change of momentum as per the rules inside this green box. The lines of code over here pointed to by these green arrows from the green box show the use of Newton's second law to calculate the net force and its components, the parallel and perpendicular components, as per the rules shown inside the green box. This line of code here calculates the distance of the star from the black hole within the loop, and then uses this distance to calculate the unknown mass of the black hole by plugging it into this formula using Newton's universal law of gravitation. Then I write the values of the time and the corresponding model computations for the net force and its components and the mass of the black hole at every observed position to the output CSV file defined in the beginning of the code. Then print the values here of the quantities just discussed upon running the Python program. I will now run my Python code to show you how it works. Notice a black sphere for the black hole, the red sphere to represent the origin, the yellow arrow representing Fnet, the black arrow representing the parallel component of the net force, and the blue arrow for the net force. This is the line of output generated by Python showing the mass of the black hole on this last position. This is a sampling of the output data written to the CSV file showing all the components of the net force, the mass of the black hole, and position and time data for the star. The net force versus time graph. Since the trajectory of the star is a smooth elliptical curve, the maximum value of the perpendicular component of the net force, shown in gold and yellow here, indicates moments in time when the direction of the star makes sharp turns to change the direction at the vertices on the major axis of the ellipse. At these turning points, the star is momentarily at rest, so delta V is 0. This is reflected by the corresponding minimum value of 0 of the parallel component of net force shown in red over here. The net force versus distance graph. The net force exerted by the black hole on the star is inversely proportional to the square of the distance between them. The blue graph shows it at the highest value when the distance between them is the least and decreases as the distance between them increases. Mass of the black hole versus time graph. Since the mass of the black hole is proportional to the product of the net force and the square of the distance between the two objects, the mass of the black hole varies with change in position of the star over time that the star takes to complete its elliptical orbit, starting and ending with the same value over here and here of 2.38 times 10 to the power 31 kilograms as the mass of the black hole. The analysis of the components of the net force and how they're different from the rate of change of momentum and its components. Newton's second law, the cause and effect perspective, helps to connect the net force of the surroundings and the rate of change of momentum. The star speeds up and slows down at different parts of its elliptical path. The non-zero velocity and momentum changes in the star's motion as the effects indicate non-zero interactions in the surroundings as the cause. The changes in speed indicate a non-zero parallel component of the rate of change of momentum. This is an effect that must have a cause according to Newton's second law, a non-zero component of net force pointing in the same direction as the parallel component of the rate of change of momentum delta p over delta t. The cause is the parallel component of the net force. Since the cause must equal the effect, the parallel component of the net force equals the parallel component of delta p over delta t. Changes in direction as seen by the elliptical trajectory imply a non-zero perpendicular component of the rate of change of momentum. There must be a non-zero component of net force, the perpendicular component of it, pointing in the same direction as the perpendicular component of delta p over delta t, causing this effect. Both these point toward the center of an oscillatory circle or a kissing circle. Since the cause must equal the effect, the perpendicular component of net force will equal the perpendicular component of delta p over delta t. Please pardon the shifting of the symbol for the perpendicular component to the top instead of being here in the subscript at the bottom. This means that the net force and its components are the causes effecting or bringing about the corresponding changes in the rates of change of momentum and its components. If the black hole is replaced by another black hole in the same position and the motion of the observed star remains unchanged and the star is affected only by the gravitational force of the new black hole, then by Newton's universal law of gravitation, the values of g, the mass of the star, position of the black hole, the distance between the star and the black hole, and all the components of the net force remain the same at every observed position. So the mass of the new black hole will be the same value as the original one. This means that if the observed effects in the system remain the same, then the causes must be the same and the new agent bringing about the effects must have the same properties as the original one. Since all data remains the same, the lines of codes in the Python model for this experiment need not be modified. To answer the lab question, no, the mass of the new black hole will not be any different than that of the original one as per the model for this lab. Thank you.